Hello students. In the last lecture, we have studied the characteristic X-rays. So we have seen how the characteristic X-rays can be produced, and the production of characteristic X-ray result into very highly intense and highly monochromatic X-rays. So we have seen that the highly energetic electron, when it strikes the target atom, it rearranges the electron inside the target atom. So, for example, the inner shell electron, it will be made free and its position will be occupied by the outer shell electron. And thereby, in this transition, a photon of characteristic wavelength is given out, and that is a characteristic X-ray. So, these characteristic X-ray, they are having very high intensity. Okay, now, but the characteristic X-rays, when observed through a very high resolving power spectrometer, it was found that they are not a single line, but they are having a fine structure. So this fine structure, how this fine structure appears, what is the reason behind this fine structure of X-ray spectra, that we are going to study in this particular lecture. So according to Mosley's observation, the line of X-ray spectrum were found to consist of two or more lines. So it is not a single line. The X-ray lines, they are having fine structure. So Mosley has performed number of experiments, and according to him, these lines are having fine structure. For example, the K alpha line, it was found to be a doublet for all elements beyond sodium. So K alpha line, it is produced, you know that whenever there is a transition from L shell to the K shell. So K shell electron has been replaced by highly energetic electron, and its position will be occupied from L shell, that is the outer shell, and the photon given out, that will be a K alpha X-ray photon. So it is also having a doublet. That means it is not a single line. So why it is so? That let us try to understand here. The X-rays line consists of two or more lines close together. This is called as a fine structure of X-ray lines. Now, in order to understand this, first of all, we have to again go to the details, whatever we have studied earlier about the spectral notation and how the terms are represented here. So the terms, let us try to understand for each of the shell in a target atom by considering the corresponding terms. Simultaneously, we shall also try to understand their X-ray notation. So spectral notations and X-ray notations, they are slightly different. So let us first of all see all these notations, and this will help us to understand the fine structure of the X-ray spectra. Okay, so the K shell in a target atom, as you know, for K shell, n is equal to 1, n is equal to 1, and L is equal to 0. So therefore, the J values is L plus S, that is equal to 0 plus half, and that is equal to half. So only one value of J is possible here, and that is equal to 1 half. So the number of levels in K shell are 2L plus 1. So we have seen this particular formula. Number of subshells or number of levels, you can say, in a particular shell are given by this formula. So for K shell, you know that the small l, the orbital quantum number, its magnitude is 0. Therefore, there is only one level. So that level is represented in terms of spectroscopic terms. It is represented as 1s half. Now 1 is used to represent the principal quantum number. Okay, so 1s half. So this level in K shell, it is represented as 1s half. Okay, now let us go to the next shell. Next shell, you know that is the L shell. Next shell, that is the L shell. And this L shell, for which n value, the principal quantum number is 2, and the orbital quantum number L will now have two values, because you know that L, the orbital quantum number, it has values from 0 to n minus 1. N is 2, therefore n minus 1 is 1. So 0 to 1, that means 0 and 1. Two values of L. Therefore the J values are. So corresponding to L value. So first of all, let us consider L is equal to 0. So the J values L plus S and L minus S. So L itself is 0. So only one value is there, that is half. So this is the value of J for L is equal to 0. And for L is equal to 1, you can find out the J values L plus S up to L minus S. So L is 1, 1 plus half, that is 3 by 2, and 1 minus half, that is half. So 3 by 2 and half. These are the two J values. So in all, we can say for L is equal to 0, one value of J, that is half, and for L is equal to 1, there are two values of J, 3 by 2 and half. So total there are three levels. So the number of levels in L shell are 3. So this is how you can just represent the J values here, and the corresponding terms are represented by the corresponding terms, that is the uh, X-ray terms. They are represented, for example, L first, L second and L third. So L first is corresponding to n is equal to 2, L is equal to 0 and J is equal to half. This first one, okay, n is equal to 2, L is equal to 0 and J is equal to half. Then L second will be for this set, that is n is equal to L is equal to 1 and J value, that is equal to this half. And L third, the same, n is equal to L is equal to 1, therefore letter P you can see here, okay. So L is equal to 1 and J is equal to half. This L3 here, okay. uh, N is equal to L is equal to 1 and J is equal to 3 by 2, and the corresponding spectral notations. So this is X-ray notation and this is a spectral notation. L first corresponds to 2s half, 2 represent the principal quantum number, and s half is this particular term, okay. For L is equal to 0, no, you know that it is represented by small s, and J value, that is half. So 2s half, that is the X-ray term, is represented by L first. Then L second is 2p half. L third is 2p 3 by 2. So there are three levels in L shell. Similarly, if you find out the levels in M shell, now for M shell, you know that n is equal to 3. So L values are 3, 0, 1, 2. And corresponding to these values of L, for L is equal to 0, we have J value is 1 half. For L is equal to 1, we have two values of J, 3 by 2 and 1 half. And for N is equal for L is equal to 2, we have two values of J from L plus S to L minus S. So therefore 3 by 2 and 5 by 2. So total you can see 1, 2, 3, 4, 5. There are 5 levels for this M shell, and they are represented by these X-ray terms M first, M second, M third, M fourth and M fifth, and the corresponding spectral terms are these. These 3 S half. 3 represent the principal quantum number, everywhere 3, and S half, P half, P3 by 2, D3 by 2 and D5 by 2. So for the corresponding J values of the corresponding L values. So L is equal to 0, L is equal to 1 here for P letter, and L is equal to 2 for this D level, okay. So there are 5 different levels for M shell. So because of these levels, now you will understand why there is a fine structure of X-rays. So because of these levels, I have shown here this detailed diagram here to understand the fine structure of X-ray spectra. So this is the K shell. Now K shell, there is only one level, and the spectral term is 1s half. We already seen that, okay. And the actual notations here represented by the quantum number n is equal to 1, L is equal to 0 and J is equal to half. This column represents the shell. These are the three quantum number n, L and J, and these are the optical notation and these are the X-ray notations. And the actual transitions I have shown here. So K shell only one level. Okay, you can assume this horizontal line here. L shell there are three levels, so they are represented by these X-ray notations: L first, L second, and L third. And we have already seen the corresponding spectral notations or optical notation. They are also called as optical notation. So 2s half, 2p half, and 2p 3 by 2 corresponding to these quantum numbers. N is equal to 2 here for all these three. L is equal to 1 here for L3, and for L2 also it is 1. And for L first, the small l orbital quantum number is 0 and the corresponding J values here. Therefore, these optical notations are shown here. Okay, now let us try to understand this fine structure. M shell, you can see there are 5 levels. We have just seen M first to M5, and these are the corresponding optical notations. Now, in target atom, whenever the highly energetic electron strikes the K shell electron and replace the electron from K shell, its position, for example, suppose is occupied from the L shell. But from L shell, there are three levels. So from which level the electron will jump over here in K shell to occupy the position. So it is very interesting. Now one has to consider the selection rules also. Okay, the selection rules must be followed. So there are three levels. So you may consider that there can be a transition from any one of these level, but this is not true. The transition is allowed from L second and L third only. Why? Because L first, you can see here that there is no transition shown from L first here to the K shell. Why? Because for L first, you can see here the optical notation is 2s half. Okay, so S half and S half here in K shell. So delta L value here 0 and here 0. So delta L according to selection rule, it must be plus or minus 1. So that condition is not satisfied here. That selection rule is not satisfied here. And J, so J should be equal to 0, delta J should be equal to 0 or plus or minus 1. So that condition, even though it is satisfied, but here delta L condition or selection rule is not satisfied. So the transition from L first to K shell is not allowed. So only these two transition from L second and L third, they are following the selection rule. See here, P to S, P to S. Therefore, delta L is equal to S and P. Here L is equal to 0 and here L is equal to 1, both of these. Therefore, you can see here L is equal to 1 and here L is equal to 0. So, therefore, delta L is plus 1. That these two transition, that means from these two levels, L third and L second to this K shell, they are allowed. Therefore, only two transitions are shown here. So because of this, there are two possibilities. The electron from L shell can either jump from L third to K or L second to K. So depending on from which level it has jumped to K shell, the energy will be different. See, the energy difference is separate or different. Energies are different. Therefore, the photon given out will be having different wavelength. For example, if you consider L third to L this K shell, that transition is known as K alpha 1. K alpha 1. It is represented by a line, X-ray line K alpha 1. Characteristic X-ray line K alpha 1. If you consider the transition from L second to this K shell, that transition is represented by X-ray line K alpha 2. It is represented as K alpha 2. So obviously the energy involved here in this transition for K alpha 1 is higher, so the wavelength is smaller for K alpha 1, whereas for K alpha 2 energy is smaller, so wavelength is higher. Now if you come to M shell, suppose the electron from M shell occupies the vacant position in the K shell. Okay, so which transitions are allowed? You can see the selection rule must be followed here. So the selection rule again for S level, that is M first, the transition will not be allowed. only M second and M third, these transition are allowed, because both of them, they are P subshells. Okay, so and this is S subshell. So delta L is 1. Delta L is 1. And what is about J? You can see here half, half. So therefore delta J 0 allowed. And here this 3 by 2 and half. So delta J will be plus 1. So that is also allowed. So these two transitions are not allowed. Again, M4 and M5 are also not allowed because they are D subshells. And D and S, see the L value. For D it is 2 and for S it is 0. So delta L will be 2. 2 minus 0, that is 2. So delta L should be either plus 1 or minus 1. So that is also not allowed. So only these transitions are allowed. And if the transitions are from M shell to K shell, they are named as, for example, M third to K shell. That is named as K beta. So shorter wavelength, higher energy, shorter wavelength. And K beta 2, it is having longer wavelength. Okay, from M2 to K shell. So this is how the fine structure arises here. So if you go to the L series X-ray, these are all K series X-ray we have seen here. If you go to next series, L series X-ray shown by blue, see the transitions. Now the transitions will be from M to L. Okay, because L series X-rays are produced when the electron is displaced from L shell and its position is occupied from the outer shell. Outer shell may be M, N and so on. Okay. So for simplicity, I have shown only the transitions from M shell. So you can see here again, only certain transitions are allowed. M first to L first, it is not allowed because the same reason, S. Okay, it is S level and S level. Delta L will be 0, so that is not allowed. Then M second, M third, both of them are P level, therefore, and this is S level, delta L is 1, therefore that is allowed. Okay, and J, the selection rule for J is also followed here. Similarly, this L2, transition to L2. See, now this is more complex because L, now it is not a single level. There are 3 levels. So transition from M to L1, transition from M to L2, and transition from M to L3. All these are possible. So you can see here 2 plus 2 plus 3. This 4 and 3, 7. Total 7 transitions are allowed. So L series you can consider here. That consists of 7 different lines. It is not a single line. There are 7 different lines. So these particular lines you can name by different letters here. Okay, you can name by different letters. So this first L alpha, then second and third, like this. You can use different letters here. Okay, you can use different letters, and these transitions are actually allowed on the basis of selection rule. So this is the reason why the X-rays have fine structure. X-ray lines have fine structure. So this is the diagram by which you can very clearly understand why X-rays have fine structure. Okay, now let us see the comparison of X-ray spectra and optical spectra. Optical spectra we have already studied earlier. For example, in one valence electron system for sodium, for hydrogen we have studied that. Then in two valence electron system we have studied for helium also, and the other atoms also we can understand the spectral terms. Now, in order to compare the X-ray spectra with optical spectra, we can consider several points. So first point we shall assume here the cause for producing optical spectra and X-ray spectra. So we have seen that X-ray spectra is produced because of displacement of the inner shell electron. So spectra is observed when there is a transition of electron from the inner shell of an atom. Whereas optical spectra, in case of optical spectra, we have seen that only the outer shell electron, that is the valence electron, is responsible. So spectra is due to transition of electron in outermost shell. So that electron is excited to a higher level and it performs reverse transition back again to ground state. So the photons corresponding to optical spectra are given out. So this is the first very important point which differentiate these two: cause for producing optical spectra and cost for producing X-ray spectra. Then if you compare on the basis of energy, definitely the optical photon has very less energy. We have seen that. Okay. So since it is the outermost shell electron, so they are having less binding energy. Therefore, the energy involved is very less. Whereas in X-ray photons have very high energy because inertial electrons are involved here in the transition process. So inertial electron, they are very tightly bound with the nucleus, so their binding energy is very high. Okay, so the third point is on the basis of their penetrating power. Since optical photons have less power, less energy, their ability to penetrate is also less. So they have less penetrating power. Whereas X-ray radiation has very high penetrating power because their energy is very high. They can penetrate deep into the material bodies. Then next point is regarding the region of electromagnetic spectrum part, which is covered by optical spectra and X-ray spectra. So optical radiation lies in visible range of the electromagnetic spectrum, and if you consider in terms of wavelength, then the wavelength is in the range of 400 nanometer to almost 700 nanometer. Then if you consider the X-rays radiation, they lies between the gamma rays and ultraviolet region of the electromagnetic spectrum. So the wavelength region is 0.01 nanometer to 10 nanometer. So this is the wavelength of these radiations. The next point you can just consider, that is the optical spectra shows abrupt periodic changes from element to element because the outermost electron is responsible here, and the atomic number, even though it is changing in a periodic table sequentially, these changes, they are actually taking place depending on the different energy levels. Whereas X-ray spectra vary very smoothly from element to element. So inner shell electron, their binding energies, they vary very smoothly with respect to the periodic table variation, atomic number variation. So therefore X-ray spectra vary smoothly from element to element. Then if you see the ability to produce ionization and fluorescence, since optical radiation has very less energy, they are not able to produce ionization and fluorescence. Whereas X-ray radiations, they are highly energetic radiation. They can produce ionization uh, and fluorescence effect in different gases or liquids. Then the optical radiation is not harmful to human body. So their energy is very less. And in the visible part of spectra, you know that human beings are quite comfortable. Whereas the X-ray radiation, they are very harmful. So any repeated exposure to X-rays, that is hazardous to human body. Now let us see some of the important application of X-rays. So in medical field, you know that there are a number of applications. So orthopedic surgeons, they are always using these X-rays, X-ray radiography to detect the uh, fractures in bone in human body. Then in material science and in especially determination of crystal structure, this is an important application. So in solid state physics, you have studied Bragg's law, and depending on the Bragg's diffraction conditions and the different techniques of X-ray crystallography, you can find out a number of parameters. You can know about the crystal structure. You can know about the lattice parameters of the given crystal of that particular material. Then a determination of DNA structure is also possible by using X-ray diffraction technique. Then X-ray imaging technique in various industries are also very useful. And the compound tomography, it is a very modern technique, compound tomography, CT, used in medical field for 3D images, producing 3D images inside the human body. So these are some important applications of the X-rays.